Okay, so this lecture is going to be everything you need to know about mixed integer nonlinear optimization. So the good news is after this class you can go home and you know everything. The bad news is you wasted the previous 3.5 days sitting through some lectures that told you absolutely nothing. So this is all you need to know, the branch and cut paradigm. If you get this, you can write your own MINLP algorithms and you can write very good solvers. Okay, so mixed integer nonlinear optimization. Again, just a quick recap. We want to solve this problem. Hopefully, by putting it up more and more, it burns into the retinas of your eyes. We're minimizing a nonlinear function subject to some nonlinear constraints in integrality on a subset of our variables. And in much of the talk, going forward, we're going to look at this linearized objective, where we use this little trick of introducing an additional variable eta that allows us to write the objective as a constraint. And then we can treat the constraints in a consistent way, and it also avoids some of the pitfalls when we generate strong cutting planes later on. And here are the basic building blocks. So you can think of MINLP algorithm as sort of Lego that you can stick together in different ways, and we'll try to show that a little bit. So relaxation is you generate a simpler problem that's easy to solve. So Ashutosh this morning showed you a MILO, a mixed integer linear optimization problem. That's easier to solve because you don't need to worry about nonlinearities. You don't need to worry about automatic differentiation or constraint qualifications. It's a much easier problem. But once you solve the relaxation, you don't necessarily have an optimal solution. So then you need to enforce the constraints that you forgot about, that you dropped. And that's called constraint enforcement. And the last building block is upper bounds that allow us to prune efficiently. So in MILO, we had the upper bounds that came from solving nonlinear optimization subproblems for fixed variables. And they help us to determine when the lower bound reaches the upper bound and we can stop solving, for example. And I'll go through all of these three with some pictures so you'll see what's going on. And then at the very end, I have a massive algorithm, but we'll just hold our breath and go through that. So a relaxation is used to compute a lower bound on the optimum objective function value. And we obtain a relaxation by enlarging the feasible set. So when we're minimizing, if you allow yourself to look further away, you get better solutions. Right? If you go shopping for a cup of coffee in San Francisco, or coffee and a donut in San Francisco, last week or 2 weeks ago cost you $22 US. That's a muffin and a cup of coffee. If you allow yourself to go to Chicago, which is a bigger feasible set, then you can get the same thing for about $12. And if you make it larger and you allow yourself to go to Italy, you can probably get it for about $4. So enlarging the feasible set gives us a lower bound. And typically we want problems that are easier to solve. So this was not a good example because if you have to run around for coffee and go all the way to Chicago, that's maybe not so easy. Constraint enforcement allow us to exclude solutions that we no longer want, so that we've seen points that we have visited already, and they refine and tighten the relaxation. And the upper bounds come typically from solving nonlinear optimization problems for fixed integer variables. So any feasible point will give us a nonlinear upper bound. Okay, so here's a generic definition of a relaxation, and this definition also holds for the non-convex part of the lectures. So it's very generic. It says we call an optimization problem where we minimize some other objective function f with this little convex quadratic function over the top of it. So that's to indicate that this is a convex underestimation over some r, which is a relaxation. We call this a relaxation if and only if the set R contains the feasible set. So it's bigger. We made the feasible set larger, and we underestimate our objective function throughout the feasible set. So an example of this would be if we have a nonlinear feasible set, and we take two linearizations, one about this point, and we can take another linearization, for example, about this point here. And that might look like this. And now if we look at the feasible set, that's a relaxation. So it's larger than the original feasible set, and it contains the original feasible set. And similar for the objective function. And we know already how to generate these relaxations. We use linearizations for convex functions. So there's a case where we can already do it. And the goal is that we want a relaxation that we can solve to global optimality so that we get a lower bound. So one way to do this is to relax the integrality. Instead of saying yi is an integer, we say yi is a real. And that gives, for example, a nonlinear optimization problem. So this is one particular relaxation that we can use. And this is used in what we'll see later on is a branch and bound algorithm. So pictorially, what you do, oh, I have a picture on the next page. Why don't I use that picture? There we go. So here are two types of relaxations. The first one is a nonlinear relaxation. So let me digest this picture first of all a little bit. There are supposed to be three nonlinear constraints, a purple, a green, and a blue one. We have two variables. The first variable is integer, can have integer points. The second variable is continuous. And so the feasible set of my mixed integer nonlinear problem is the union of these red lines, right? I have to be integer, so I have to be on one of those integer points, and I have to be inside my feasible set, and that's that line is in it, that line, this line, and this line. So you see that's clearly a non-convex set. It's the union of these four lines. And I can relax it non-linearly by relaxing integrality. So if I relax integrality, then I end up with a set that's the pink set up there, which is now the one of the first variable is now allowed to be continuous, and the second variable was continuous anyway. But I can do a different relaxation. I can create outer approximations, which is what I did here. So I just added three cutting planes, and now I enlarge the feasible set in a different way. But here the feasible set is still the union of these now 5 red lines. So something interesting happens here, that when you do this, you sometimes find that you get an additional integer point that wasn't feasible over here. And I can relax this further. So this is what I actually did here. If you now take the convex hull of these, well, or if you relax integrality in this problem, then you get the pink set. So there's hierarchies of relaxations that I can take, and we're going to look through all of these in a little bit. So we can combine these relaxations, and we're going to do this. And so, for example, if we construct convex underestimators of non-convex functions, then we can relax them further via supporting hyperplanes. And there's a fundamental theorem that helps us, that says why relaxations are good. And that's if the relaxation of my MINLP is feasible in the original problem, then it also solves the original problem. And so, for example, if I take the relaxation where I relax integrality, and I solve that, and the solution is integer, then I know I solved the original problem. So that's really cool. That never happens. So there are some example problems where it happens, but it's very, very rare. Okay, so the second step, so this is relaxations. Relaxations give us lower bounds. They relax integrality or nonlinearity. Now we need to go back and enforce the constraints that were relaxed in a systematic way. And so now what I want to do is I want to take the solution of a relaxation x hat y hat that is not feasible in my mixed integer nonlinear problem, and I want to exclude it because I know it's not a solution. So I'm going to generate a cut or do something that prevents me from going back to this point. And so the things I can do is I can tighten my relaxation by somehow refining it. I can branch on a variable or on another constraint, and that again can exclude non-integer points. And later on in the course, we're going to talk about spatial branching, where we also branch on the non-convexities or the relaxations of the non-convexities. And these are very flexible. We can combine them. And in the first algorithm, I'm going to just put them all together into one big mishmash of algorithm. And then we'll tell you how to take them apart again. Okay, so here's one way of doing this constraint refinement. So for example, we can add a valid inequality to the relaxation. So here we have a relaxation, a polyhedral relaxation. So this will be an MILO, a Milo relaxation of my nonlinear problem. I've forgotten, there's an integer here too that I forgot, so that should be written there as well. And assume that the objective function is trying to push you into this direction towards the bottom right, then the optimal solution would lie here, right? It has to be integer, which is why it's not there, and this is the lowest point for my optimum solution value. But this point here violates this green nonlinear constraint because I relaxed this nonlinear constraint with my linearization. So this constraint is not valid, but I can do my trick. I can now solve a nonlinear optimization problem, which is what I would do in outer approximation. And I basically walk up to this point here. So if I fix my integer variable to be along this line, then the minimum would maybe be here. That's sort of in this example, that's how I cooked it up at the intersection. And now this new hyperplane cuts off this point. So this point is no longer feasible if I now solve this new relaxation. So I will not go back to this point. And that's what we showed was the optimality lemma. And for the infeasibility lemma, there's a similar one. So you can't go back to this point because you tightened this relaxation. Okay, so, and so these valid inequalities are called cuts because they cut off infeasible solutions that are not valid. They're used in Bender's decomposition or outer approximation. We'll tell you what these are. And they're also the basis for branch and cut techniques, though they are a little bit more sophisticated than the ones that I showed here. There's an alternative way to do constraint enforcement, and that's branching. So branching is something that I do if I have continuous relaxation. So I relax the integrality constraints on my integer variables. So now assume that I solved some relaxation and I found that my solution lies here, which is not integer. It's between these two integers. And then I know that the true solution to this problem has to be either below this value here or above the ceiling of that integer variable. So I can add two cuts or branches where I say I'm above the ceiling of my integer variable that was fractional, or I'm below the floor of that integer variable. And so those are two new nonlinear optimization problems that I now created. So I started off with a continuous relaxation. Now I have two subproblems that I need to solve. But notice that the feasible set of my mixed integer nonlinear problem is still contained in the union of these two problems. So the feasible set is either these two lines here or these two lines there. So I haven't done anything that's illegal or that would just prevent me from finding the true solution. Now I just have to solve two problems. Unfortunately, if I repeat this, I could create a big branch and bound tree. And this is what sort of is the basis for branch and bound, that we branch create this disjunction on one of the integer variables at a time. You can also branch on multiple integer variables. So for example, for special ordered sets, you branch on subsets of the integer variables. And there's other ways of branching. Okay, so this is all leading up to the generic nonlinear branch and cut algorithm. So I might scare you on the next slide, but rest assured that we will come back to this algorithm many times. And if I don't scare you, then that's good, because you can go away and implement it. Okay, so for this mixed integer nonlinear optimization problem, I'm going to define a particular subproblem in which I relax the integrality. So in this problem, y is no longer an integer, it's now a continuous variable. It's a nonlinear optimization problem, but it has got these two additional parameters, L and U. And L and U are these lower and upper bounds. And so where do they come from? They come from this operation here, because here I added a new upper bound for this problem. For this problem, I added a new lower bound. And you can imagine if you keep doing this, you keep adding bounds, you change these bounds on these problems. And the branching cut algorithm combines both the branching, so that's why I have this problem here, and the cut generation that we had earlier, the cutting planes that are generated into a single mixed integer nonlinear optimization framework. Okay, so here it is. This is a lot to take in. We'll try to digest this, or I'll try to digest it. It takes me a long time to digest this too. So the first thing is we have a heap. That's a way of storing nonlinear optimization problems. We're not storing the nonlinear problems. All we're storing actually are the bounds, or the changes in the bounds that we need to store. And Pietro and Ashutosh can tell you much more about the details on how this is done effectively. So initially, you put the initial problem you place on there doesn't have any lower and upper bounds. So you just set them to minus infinity and infinity, which means if I set these two bounds to minus infinity and plus infinity, then that's just the continuous relaxation of this problem that I had up there. So if these are infinity, then there are no bounds. So that's the initial problem that I put on my heap. And then I keep, as long as this heap is not empty, I keep doing this double loop. So as long as the heap is not empty, I pick any problem from it. So the first problem that I pick is the continuous relaxation, because there's nothing else on it. That's the first problem that I placed there. So at the first iteration, I pick up this continuous relaxation. And guess what I do next? I solve this continuous relaxation, and I get a solution that I now label x, y with LU. So it corresponds to this particular choice of lower and upper bounds. Okay, and if this problem that I solved there is infeasible, if there's no feasible solution, then if I add more cuts or branch on it, I will add more constraints. I will just make it more infeasible, if this were possible. So if it's infeasible, then I can prune the node, declare it infeasible. I never need to look at this node again. Otherwise, I'm going to compare it to my upper bound. So if it's larger than my upper bound, then I know I cannot find a solution. The upper bound is going to collect the best solution that I've found so far. So if it's larger than the upper bound, then I'm not interested in finding, I'm not going to find a better solution there. And then crucially, if the binary or the integer variables are actually integral, then I can update my incumbent. So I now have a new best point. So my new upper bound is then the solution that I generated. And otherwise, I'm going to generate some cuts. And for example, outer approximation cuts. And I can keep looping around this until I don't want to generate any more cuts, or I'm done generating cuts. And if it's not pruned and there's not a new incumbent, then I can branch on a variable. So I can either generate cuts or branch on a variable. So in a sense, this algorithm, what it does is it collects problems that are in this branch and bound tree. It picks a problem. It either generates additional cuts to make it tighter, or it branches on the problem, in which case it generates 2 new subproblems and puts them on the heap. That's what this function does down here. So it's a way of managing subproblems, and we keep doing that until there's no more problems to explore. And once there are no more problems to explore, then we either have a solution if we went into here, or if all the problems were somehow infeasible eventually, then we have an indication that the overall problem is infeasible. Okay, so this is, I'm going to show you some instances of this algorithm over the next couple of lectures, and then it'll become more apparent on what's going on here. These trees can get large, so the tree that I had earlier, there were 2 nodes. There can be tens of thousands of nodes. And in the remainder, there's a little exercise. So you can do this now. Get a piece of paper out, or your iPad, or ChatGPT. So given that you have an integer that is a p-dimensional integer, what is the maximum depth of your tree? So in your tree search, in this case, what you do is you generate nonlinear problems that corresponds to nodes on the tree by either picking a variable and either setting it to 0 or setting it to 1. And then you would pick another variable and set it to 0 or 1. And so the question is, how far do you have to go until there's nothing more to do, until all of them are either fixed at 0 or 1? That's the first question. I'm not sure. Is this question clear, or should we come back to this in the next lecture?
What is the size of I?
Ignore I here. That's a typo. Ignore I. Sorry? Okay, good. Excellent. So P, that was easy. It's something like 2 to the power T. P. Well, so what's the size, Ashutosh? It's not 2 to the power P.
It's more than 2 to the power P.
Right.
Your number of leaf nodes are going to be 2 to the power P.
So at the bottom here, so you keep going, and you can do this P times. At the bottom, there are 2 to the P problems, because if you have a 0, 1 variable of size P, there's 2 to the P combinations, and each one corresponds to one of those. So then the question is, how many problems are there on the next level up? 2 to the power P minus 1. Okay? Okay, so then we need to sum all those up to get the total number of nodes in this tree. But to first order, it's 2 to the P. If you're not, yeah. These are much smaller numbers than 2, maybe. Okay. What if I had, so going back to the branching, let's go back to branching. There we go, branching here. So in this branching example, I have a general integer variable, and this integer variable is 0, 1, 2, 3, 4, 5, 6. Say it's between 0 and 6. So let's assume I have an integer variable. So I have y is in 0, 1, 2, up to 6. And so here I did the branching in this example. My y hat, the initial point there was something like maybe 3.4. So the way I branched was to say, here I said y is less than or equal to 3, so that's the floor. And here I said y greater or equal to 4. Right, and that started generating my tree. But are there other ways how I could have branched here?
We can branch like y equal to 0, y equal to
Yeah, exactly. You could do, so this would go, this is sort of a binary tree, but you could also do an n-ary tree. So then you start off and you say y equals 0, y equals 1, up to y equals 6. I think people tried this in the early days, and people proposed that this is maybe a good idea, but it's not really, I don't think it's that efficient. And, but we can sometimes potentially explore some of those nodes tentatively to see if there's anything where we can fix anything. That's it. Those were the questions. So, and so after lunch, we'll talk about nonlinear branch and bound, which is a simpler version of this branch and cut algorithm. And then tomorrow we'll have a different version of the branch and cut algorithm. So we'll be talking about this framework throughout the lecture. But the three fundamental things that you hopefully learned, or you now know, are the three fundamental building blocks for mixed integer nonlinear optimization algorithms: relax, enforce the constraints, and use upper bounds. And with those three things, you can go away and build your own new solver over lunch and write a paper and become famous. Excellent. So, do you have any questions?
Sir, is there any specific type of general cuts? We are talking about general cuts.
How to generate cuts, specific ways to generate cuts. So we saw one way of generating cuts, which were the outer approximation cuts. So that's one example that we've seen. There are many other ways for generating cuts, and we will look at those over the next 2 or 3 days. And a lot of the cuts exploit problem structure or characteristics of the functions that we use.